Hi all, my name is Carol and I'm a fifth year PhD student in EDIC. In this presentation, I'm going to show you some of the work on traffic analysis protection that we do in our lab. The doc in this video doesn't actually follow the correct cup. Instead, it uses a side channel. In this particular case, the smell of a treat to guess which cup has the desired content. This video is a metaphor for another side channel that exists in the human world. And this is a leakage of metadata from encrypted communication. Most of the communications that we do nowadays is encrypted, be it talking to your friend over Skype, streaming Netflix videos, watching this particular video on YouTube, or sending WhatsApp messages or encrypted emails. However, these encryption schemes tend to only protect the content of our communication, leaving some important metadata in clear. And this metadata can be the traffic patterns, for example, the ratio of incoming and outgoing packets, the size of the object that we send, and parameters of the encryption and the recipients of that. And researchers have used this kind of metadata to actually infer the encrypted communication. In this particular example, Schuster et al. Demonstrated how to identify videos being streamed. And the key insight is that bitrate depends on how much action happens in the video. More action, more bits being sent. And this information was sufficient to uniquely identify a big corpus of videos. Similarly, Wright et al. Showed how to use length of packets to recover first the spoken language of voice over IP traffic, and second, how to identify spoken phrases. And the idea here is that different sounds that we produce require different amount of bits to be transmitted. For example, vowels, in some reason, are more complex to transmit, and silent consonants are easier to transmit. And later on, White et al. Actually showed how to derive full approximate transcript for the whole conversation. And here's an example of clear text encryption parameters. OpenPGP is a popular format for encrypting files and emails. But in addition to the encrypted payload, it reveals information like a recipient key ID and public key algorithm in a clear text header. And sometimes an adversary can use this clear text metadata to simplify the job of cracking the algorithm. So the question is, how do we protect ourselves against all these attacks? So far in EDIC, we focused on eliminating the last two sources of metadata leakage, is object sizes and encryption metadata. And to do so, we designed a new format for ciphertext or for encrypted data, which don't have any metadata in clear. And we call it padded uniform random blobs. And the idea is that a padded blob would include both content and metadata, and would be indistinguishable from some random bit string to someone without the encryption key, as the leakage via its length would be minimized. And to enable creation of such padded uniform random blobs, we designed two schemes, one for encoding and the other one for padding. Interestingly, the main challenge for designing an encoding scheme was actually decoding, and in particular, how to make it efficient when you don't have any metadata in clear text. And it is especially challenging when you send that ciphertext to multiple recipients, and they might use different cryptographic algorithms. And in our scheme, we use some combination of symmetric key and public key encryption, and data structures like the hash tables, and some XOR mixing to make it efficient for any number of recipients and for any number of cryptographic schemes being used. The main challenge in designing a padding scheme was to find the sweet spot between effectiveness and the overhead. And both previous work and our work show that padding to a fixed block size is essentially ineffective, but padding exponentially is expensive. It results in a high overhead. So our solution was to pad exponentially and to have padding as a function of size, but also to introduce finer granularity. So in the result, we achieve the same asymptotic leakage as exponential padding, but the real numbers of the overhead are much lower. In addition to the work I've talked about so far, we're also interested in building other privacy-preserving systems and data. And it could be privacy-preserving backup systems, can be metadata protection and security protocols, private information retrieval, or anonymous communication, and of course, much more. And if you're interested to know more about the project I talked in this presentation, you can go to the website probes.net, or if you want to ask anything, you can just send me an email or contact me on Twitter.